We are talking about transformations of quadratic functions, and we want to describe transformations of quadratic functions, write transformations of quadratic functions, and write equations of quadratic functions in vertex form, given the vertex and a point. So the parent function of a quadratic is y equals x squared. The parent function of a linear function is y equals x. So basically, whenever we're talking about the parent function, we want the most basic version. So the most basic version of the quadratic function is y equals x squared. Most basic version of a linear function is y equals x. And so although we have the most basic version, we can also do transform and scale. So the a value will scale the function, and the h and the k will transform or translate the function. So hk is the vertex of the parabola. X equals h is also the axis of symmetry. So if we look down here, our parent function is f of x. This is the black function right here. We have our vertex, which is located at 0, 0, and we have a line of symmetry that goes right through the vertex, and it splits the parabola into two even parts. The h shifts the graph along the x-axis to the right and to the left. So if h is less than 0, it shifts the graph to the left. So in other words, if h is negative. If h is greater than 0, it shifts the graph to the right. So in this case, if h is positive. Here's a note. H looks backwards because the negative sign in front of the h in the original equation. So because of this negative sign right here, if you substitute in a negative value, x minus -2, negative becomes positive, so it actually looks like it is a positive. So it looks backwards. K is straightforward. K shifts the graph in the y-axis up and down. So if k is less than 0, shifts the graph down. So if k is negative, shifts the graphs down. If x is greater than 0, it shifts the graph up. So if x is positive, it shifts up. Here's the parent function, f of x equals x squared. That's this black function right here, and we can see that it has the vertex at 0, 0. G of x equals the quantity x minus 2 squared. It looks like it has a -2 here, but because of the negative value, we're actually substituting in a 2. So, and there's no change to the y. So there's no vertical shift. There's only a shift 2 to the right. 1, 2. So right there. So the vertex becomes 2, 0. If we look at j of x is equal to x plus 4 quantity squared, this looks positive, so we should think, oh, shifting to the right, but it's not, because in order to make that become a positive, we actually had to substitute in a -4. So shifting to the left, 1, 2, 3, 4. And then we have our last example here, the green function, where we have x squared minus 3. There's no horizontal shift, so we're not shifting to the left or to the right because there's nothing inside the square next to the x, and we only shift 3 down. So 1, 2, 3. So we can take a look, and we can see that the parent function is f of x equals x squared, and we have the vertex at 0, 0, and then we have other points. We go over 1, up 1, and we have a point right on the grid, 1, 1. And we also have the point if we go over 2, 2 squared is 4. So we go 1, 2, 3, 4. So we have the point 2,4 that also lies on the graph. So from the vertex, to get to that point, we go over 2, up 4. So we can take a look. And here we go to the right 2, 1, 2. Now from this spot here, in order to get to this point, we can go to the right 2, 1, 2, up 4, 1, 2, 3, 4. Even though that looks negative, remember the x is backwards. Now we take the parent function and we don't shift it any direction. We don't shift it in the x direction at all, but we simply shift it down 3. 1, 2, 3. So then we get the point 0, -3. And then the last one we have here, we have x plus 4, quantity squared. So we're going to shift it to the left. 1, 2, 3, 4. And we get the point 4, -4, 0. And we can see that if we count over 2, up 4, 1, 2, 3, 4, we still have that point at -2, 4. 2 to the right, 4 up. Also, we could go 2 to the left, 4 up, and still have that same spot because the graph is symmetric. One other thing that we have to talk about is we have to talk about our A value or our scale. So the scale factor of the parabola is the vertical stretch and vertical shrink. As A gets larger, the graph gets narrower or rises faster. A cannot equal 0. If A was equal to 0, then this whole thing would drop out, and then we just get the function y equals k. And that is not a parabola. If A is less than 0, it's concave down. So if A is less than 0, that's a negative. So in this case, we have the function here, we have -2, so we see that the parabola opens down. If A is greater than 0, it's concave up. So if A is positive, concave up. If the absolute value of A is between 0 and 1, can't be 1, that's the parent function, can't be 0 because then it's a line. So this would be like a fraction, so 1/2, or a decimal. Another example could be like 0.03. Okay, so anything, a fraction or a decimal, we're looking at the graph getting wider. So here we have m of x equals 1/2 x squared 1/2. The parent function here goes over 2, up 4. 1, 2, 3, 4. And m of x says take that parent function and cut it in half. So instead of going up 4, we're only going to go up 2 to right there. For the other one, for n of x equals 2x squared, what that does is that makes the graph rise faster. So we go over 1, up 2 for the parent function, or we go over 1, up 2 for n of x. And we can take a look at that on the graph. So we can turn these shifts off and we can look at the scale factor. So we can see that the scale factor of 1/2 widens that graph or gets it closer to the x-axis. So we can go over 2, up 2, cut it in half. Or we can go over 2, over 2, up 8, because the graph has been stretched by double. So normally for the parent function, we go over 2, up 4, but because of our multiplication of 2, that is going to move the graph up to 8. Then we also have -2. So the -2 does the same thing as the red graph does, except for it moves it so that it opens down. So we go over 2, down 8.